All right, hello Algebra 2 people. 6.4, use inverse functions. An inverse relation interchanges the input and output values of the original relation. An inverse relation interchanges the input and output values of the original relation. So we can actually explore this idea three different ways. One way is with the table of values, another way is with a graph of those coordinates, and then a third way that we're going to spend a lot of time with is as actual equations. So let me give you an example here. If you'll write original, and I give you a table of values, and I say that the original table of values, your input of 0 gets you an output of 6. Input of 1 gets an output of 4. 2 to 2, 3 to 0, 4 to -2. Okay, now if that's the original, the inverse table would interchange the input and output values. So instead of having 0, 6, we're going to have 6, 0. Instead of having 1 to 4, it goes 4 to 1. 2 to 2, 0 to 3, -2 to 4. And that's all there is to it. If you have a relation represented as a table, to get the inverse, you just swap the x and y values. Well, graphically, this looks kind of interesting, I think. Let's see, all I've got is my pencil here handy, so I'll have to make do. But let's plot these points here. 0, 6, 1, 4, 2, 2, 3, 0, and 4, -2. Well, look at that, class. It appears to form a line, doesn't it? You actually could tell that if you look, the zeros are consistently going up 1, the y's are consistently going down 2. So notice our slope is down 2 over 1, down 2 over 1. It's kind of a cool relationship. All right, so that's our original function. And now I think I'll use like x's instead of points to denote my inverse function, just to kind of keep track of things. So 6, 0, 4, 1, 2, 2, 0, 3, -2, 4. All right, so we've got our original coordinates, we've got our inverse coordinates. Well, it turns out these coordinates are connected graphically through one transformation, okay? Now, this one transformation is in fact a reflection. Now, up to this point, we've looked at some reflections in functions, but we've mostly talked about reflections across the x-axis. If you put a negative out front of a function, it'll reflect it across the x-axis. But that's not what we have going on here. If it was a reflection across the x-axis, we'd have x's down here somewhere, but they're not. They're okay. So turns out, I'll cut to the chase. Inverse graphs are reflections of the original graph across y equals x. And y equals x is this diagonal here. So I'm just going to draw a dashed line going across here. So what you can see is if I go reflect across this y equals x here, it's going to put me equally spaced on the other side, and there's our corresponding inverse value. Notice 2, 2 was on our line of symmetry, and so it doesn't move anywhere. It's right there. So this can help us out. It gives us a better understanding of what's going on. The graphs. Oh, let me slide that up. Sorry. The graphs are reflections across y equals x. And that's always the case. Which is pretty handy to know. All right, now we haven't talked about equations yet, so let's get into that. To find the inverse of an equation, using x and y. To find the inverse of an equation using x and y, you switch the roles of x and y, and then solve for y. And solve for y. So again, this idea of, the x and y value switching. Okay, let me show you what we're talking about here. Find the inverse of the relation, and we've got y equals 4x plus 2. Well, we're going to swap x and y. And we are going to solve for y. Subtract a 2 over. Divide by 4. Now keep in mind, when we multiply or divide, we need to, ideally we'll distribute across addition and subtraction. So that's what I'm going to do here. I'm going to divide both of them. So I get a value. I'll put the y out front just because it's more customary, but I'll get y equals, and you'll see it written like this. You'll see it written as 1/4. Whoops, too much lead. 1/4 x is one way to write it. Personally, I don't mind if you write it as x over 4, but you'll see people move that fraction out to the front, leave x down on the ground. So you'll have 1/4 x minus a half. Now notice every operation in the original function is its inverse operation is in here. Multiplying by 4, dividing by 4, or multiplying by the reciprocal, adding 2. Well, this is kind of a curious thing. We've got adding, so we've got subtraction, but instead of a 2, we've got its inverse, 1/2. So it's interesting how it's all in there. If you look up here, you see the minus 2 in there in the dividing by 4. So the inverse operations of each operation can be found. All right, let's move on to one that's in function notation. Well, first thing, we'll just get rid of that function notation. And now we can swap x and, oh, whoops, sorry. I had that hidden, didn't I? I'll swap x and y. Subtract 1 over. Distribute my division. And I get y equals negative 1/3 x plus 1/3. Negative divided by negative plus 1/3. And there we have it. Inverse of a relation, inverse of a function. All right, let's flip the page over, see what else we got. All right, next up, we're going to verify that functions are inverse functions. And initially you might think, well, if somebody asked you to do this, verify that these are inverse functions. You might think, okay, well, I'll swap x and y for one of the equations and then solve for y. See if it matches the other one. I like that. That's a very intuitive way of doing it. But turns out there's another way to do this, another way to verify these functions, and we need you to be aware of how to do this. And let me write out what you're going to do up here at the top. You can verify functions are inverses by finding their composites. You can verify functions or inverses by finding their composites. If both composites, if they both equal x, they are inverses. This is kind of a curious thing. Let's suppose you've got, you're given f and you're given g, and you want to find out if they're inverses. Well, you'll do f of g of x, that's the composite function, and you'll work it out, you'll simplify it, and you'll get x. But you also have to do both. You also have to do g of f of x, the other composite function, and work that down and verify that it is equal to x. If you have both of these, then you know they are inverses. Well, it's kind of interesting. I got to be honest with you. I have a tendency to rush through these next two examples. I feel like they're really clear, but then when I think about it more, I think about how the order of operations really can get confusing on these. So I'm going to take my time going through these, and you might want to pause these and back it up to, if you need to, if you're having trouble following why one step is first. Okay, we've got a little bit of notation here you may not be familiar with. We've got f of x equals 4x plus 2. And this is saying f inverse of x. Okay, so they're saying straight out that this is the inverse of this. We need to verify that they are inverses, okay? And so to do that, we're going to do the composites. We're going to do f of f inverse of x. We're also going to do f inverse of f of x. So remember, composites are like a function swallowing another function. And then we carefully write these out. Now, you're going to often have two sets of parentheses, okay? If you don't have two sets of parentheses, or you have one set of parentheses that isn't closed all the way, you're probably doing something a little bit mistaken, okay? So let's see. We're going to take this f inverse, put it in right there. So we'll go 4, and then we'll go parentheses, and we'll write out 1/4 x minus 1/2. And then close that parentheses, plus 2. Okay, so we're in luck. We only have one set of parentheses here because neither one of these functions started out with a parentheses. So I think we're in good shape. We put all of the inverse values in for x. And now it's a matter of order of operations. We know that we're supposed to get x, but we need to verify. We need to prove, showing our steps, that it does in fact equal x. Now what I mean by that is, if you just go straight to x and say x, ta-da, you're not going to get credit for that, okay? I'll be very clear about that. You got to show some steps. Show me what you're doing first. Show me what you're doing second. For example, if you cross these out and say those undo each other, for one, that's not true, but also that's not correct order of operations. The correct order of operations would be to multiply this 4, distribute that 4 first. And if we do that, we get x minus 2. And now the parentheses is no longer necessary. We've got plus 2. And now we can bring it down to x. But we had to start out with distributing first. You need to show me that. Okay, so far so good. Now we'll go to the other side. So we're taking 4x plus 2, placing it in for x. 1/4 4x plus 2 minus 1/2. kind of double check. My parentheses are closed up, should be in good shape. And again, we're going to distribute first. X plus a half, no longer need the parentheses, minus a half equal to x. Since we have both, yes, inverses. All right, let's move on to another example. Verify that f and g are inverses. So we're going to find f of g of x. We're going to do g of f of x. Oh, let's see. No, I better not pause it. Never mind. Sorry, the washing machine stopped, and I always got to try to get the laundry done before the week starts. Me and my wife, that's kind of our goal. Get that laundry done before the week starts, or else you're kind of behind. But anyway, so f of g of x, we're going to write that. So we've got, let's see, this all going into that x right there. So I'll go 5 parentheses, and I'm going to write everything. So parentheses x plus 2 over 5 to the 1/2 power. All that inside the parentheses that I used in place of x. Outside of that, I got a squared and a minus 2. There's a lot going on. Notice we had a restricted domain on this because you got a even exponent in there. When you do the inverse, you'll have to do a root, and so it was greater than or equal to 0. That's why this is just a plus here and not a plus or minus. But you had that restriction. That doesn't impact our composite functions at all. Now take a look at this. Order of operations is a little bit tricky. Order of operations, you've got parentheses. You've got another set of parentheses. Now there's nothing we can do inside this parentheses. Then you go outside the parentheses, you've got an exponent. Outside of these parentheses, now this 1/2 does not go to this x and this 2 and this 5. That it doesn't. There's no property of exponents that say that exponents travel across addition and subtraction. So we've got nothing to do here until we look on the outside of this parentheses. Then we've got a choice to make. Do I multiply this 5, cross those out? Or do I do this exponent of 2 and cross those out? You can't, it's not an either or. You have to do one. Only one is correct. And think of order of operations. Parentheses, exponents, then multiplication. So we're going to do this exponent property first. And after that, you no longer need that outer parentheses. You can just go x plus 2 over 5, like so. And I think we've dodged the bullets. We're in good shape here. 5s will divide out, and we'll get x plus 2 minus 2, and we're there. Whew, okay. G of f of x, all of this is going in for x. So we go parentheses, 5x squared minus 2. Close parentheses, closing the x. We've got a plus 2. It's all over 5 to the 1/2 power. Again, order of operations. Go inside this parentheses. Go to this parentheses. Can't simplify anything. We've got a fraction. You want to fraction acts as a grouping symbol. You want to simplify this numerator first. And when you add those together, those 2's, they'll undo each other. At that point, the internal parentheses is no longer necessary, so you'll have 5x squared over 5. 1/2 power out there. It's very tempting to cross out those 1/2 powers, but again, order of operations, we still need to do what's inside the parentheses. So the 5's divide out next. And on this example, the last thing you do is to do that property of exponents and multiply those together to get x. And they both work checked out. So yes, inverses. Now take your time when you simplify these, okay? Take your time. You're going to want to practice. The practice is page 443, numbers 3 through 21 odds. All right, thanks so much for watching. Have a great day.